Gibbs free energy. Let's review a few things we learned in the last lesson about the Gibbs free energy. Minus T delta S for the universe is defined as the change in Gibbs free energy delta G. When delta S for the universe is positive, delta G is negative. Therefore, for a spontaneous process, delta G is negative. The equation for finding the change in Gibbs free energy is delta G equals delta H minus T delta S. The sign of delta G tells us whether a particular process is spontaneous. For a chemical reaction, the value of delta G tells whether the reaction is spontaneous as it is written. Let's look at the value of the free energy for the well-known reaction N2 gas plus 3H2 gas in equilibrium with 2 NH3 gas, the ammonia equilibrium. The diagram shows the value of G for various compositions of a mixture of the three gases at some particular temperature, starting at the left with all N2 and H2 and no NH3, and ending on the right with only NH3 and no N2 or H2. If delta G is negative, then the forward reaction is spontaneous. As we start from the pure N2 and H2 and make some NH3, moving toward equilibrium, the value of G decreases and delta G is negative. So the reaction is spontaneous, moving from only N2 and H2 toward equilibrium. If delta G is positive, the reverse reaction is spontaneous. If we continue to increase the amount of NH3 towards the right of the diagram, the value of G increases, and going the other way, that is, the reverse reaction, is spontaneous. So the reaction is spontaneous, moving from pure NH3 toward equilibrium. When the value of G is a minimum, then delta G is positive, going in either direction away from the particular concentrations of N2, H2, and NH3, and we are at equilibrium. At that point, delta G equals 0. So if delta G equals 0, then neither the forward reaction nor the reverse reaction is spontaneous, and the reaction is at equilibrium. This is one of the most important little facts to remember about free energy. Anytime a system, a chemical reaction or a physical change, is at equilibrium, the value of delta G is 0. Like enthalpy, and unlike entropy, it is impossible for us to know the exact value of the free energy under any conditions. So, like the enthalpy of formation, delta H sub F 0, we compile a list of the free energies of formation, delta G sub F 0, to use to calculate the value of delta G 0, because G, like H and S, is a state function. We can then estimate the value of delta G for a reaction in the same way we find the enthalpy change, delta H, for a reaction, by using the standard free energy of formation for the substances. The equation is delta G for the reaction equals the sum of N times delta G for each of the products minus the sum of M times delta G for each of the reactants. The N and M are the coefficients in the balanced equation. However, we can also calculate the value of delta G at a particular temperature from the values of delta H and delta S by using the equation delta G0 equals delta H0 minus T delta S0. How does the value of delta G0 change with temperature? That depends on how the temperature changes and on how the values of delta H and delta S change with temperature. There are two parts to the delta G equation. The enthalpy term, delta H, and the entropy term, T delta S. If we assume that delta H and delta S do not change much as the temperature changes, which is not exactly true, but is not a bad assumption as long as the temperature does not change too much, then we can see that the way delta G changes will depend on the sign of delta S and on what the change of T is. In particular, if delta S is positive, then an increase in temperature will increase the value of T delta S, and, because we're subtracting a positive value from delta H, will make delta G decrease. That is, it will make it less positive or more negative. A decrease in T will increase the value of delta G. On the other hand, if delta S is negative, then an increase in T will increase the value of delta G, and a decrease in T will decrease the value of delta G. Does this make the process spontaneous? Well, that depends on the sign of delta H as well as the sign of delta S. The four possibilities for combinations of sign of delta H and sign of delta S are summarized in this table. If delta H is negative and delta S is positive, then delta G will always be negative no matter what the temperature, and the reaction therefore will always be spontaneous. If delta H is positive and delta S is negative, then delta G will always be positive no matter what the temperature, and the reaction will never be spontaneous. If both delta H and delta S are negative, then delta G will be negative below a particular temperature and positive above that temperature. So the reaction will be spontaneous below that temperature and not spontaneous above that temperature. The particular temperature depends on the reaction. If both delta H and delta S are positive, then delta G will be negative above a particular temperature and positive below that temperature. So the reaction will be spontaneous above that temperature and not spontaneous below that temperature. In both of the last two cases, at the particular temperature, the system will be in equilibrium because delta G will be zero. Remember that when we use the table to calculate delta G0, we are doing this under standard conditions. That is, each substance is in the physical state it has at 25 degrees Celsius, the pressure of all gases is 1 atmosphere, and each substance in solution has a concentration of 1 molar. What happens when we're not under standard conditions? A fairly common event. We can calculate the value of delta G under non-standard conditions by using the equation delta G equals delta G0 under standard conditions plus RT natural log of Q. Note here the absence of the little circle for the first delta G. Here, Q is the mass action expression we have already used to determine the direction an equilibrium system will move. Note that when we are under standard conditions, all pressures are 1 atmosphere and all concentrations are 1 molar, so the value of Q is 1. Since the natural log of 1 is 0, the last term drops out and delta G equals delta G0, as it should. If we are at equilibrium, then we know that the value of delta G is 0. We also know that the value of Q equals K. Substituting into the above equation, we get 0 equals delta G0 plus RT natural log of Kp. It must be Kp if there are any gases present. If there are no gases, then it doesn't matter. If we rearrange the equation, we get a relationship between the free energy change under standard conditions and the equilibrium constant, which almost certainly occurs under non-standard conditions. This is a tremendously useful relationship, so remember that it exists. The relationship is delta G0 equals minus RT times the natural log of Kp. Or, if we want to calculate K, Kp equals e to the minus delta G0 over RT.